I just added another little paper. We've been talking a bit around the area called ergodic theory. This is a nice review. It actually is quite old. It's from 1973. But very readable. It was in Physics Today. And at the end of the lecture, I'll come back to talking a bit about ergodic theory. So today what I want to do is introduce how we're going to adapt information theory to start describing information and the complexity of stochastic processes over discrete alphabets. Then I want to come back to, well, basically that'll allow me to introduce one of the key so-called invariants or properties of any stochastic process, its entropy rate. And that actually kind of ties back in with a little bit of the history of ergodic theory, going back to Poincaré and Boltzmann and so on. This article gives a nice historical summary that kind of backstops some of the comments I'll make. Should be fairly readable. Okay. Okay. So for Cover and Thomas, we're doing pretty well. I mean, you might have noticed I've tried to give selected readings. We are hopping around a little bit. They have slightly different needs, right? So the very first lecture was just covering Chapter 2, what's Shannon entropy, what's a mutual information, what's an information gain, basic ideas. And now we're starting to apply those things. There is this, it's interesting, in the second edition, they moved this chapter on the asymptotic equipartition property to Chapter 3. It might come off as a little bit technical, but it's a really short chapter. It's worth reading. It's kind of deep, actually. And we'll come back and kind of allude to the properties without doing the same formal development that Cover and Thomas do. So it might seem a little bit strange there, but sort of the main idea is the entropy rate tells us how big the set of sequences is that has the most probability, which is a handy thing, right? So remember, one of the problems we have right now is we have processes, and they generate words, and now we attach words to them, the word distributions. Now, when I first introduced Shannon entropy, I kind of emphasized that, well, we don't have to carry around in a description of a process this bag, in principle, a bag of infinite number of probability amplitudes over infinite number of words. There's this scalar. So we're mapping from the entropy maps from a distribution to a scalar, and the question is, how much can we learn from this entropy scalar about the structure of the process? Obviously, it's throwing a lot of information away if I just have a number, but it did give us some geometric properties of any event distribution, right? The higher the entropy, the more uniform the distribution over the event. So they had a kind of a geometric interpretation. Now, the problem we're confronting now is we want to go to processes where we're looking at words, which, like the fair coin, the number of words that a fair coin generates, that grows exponentially, right? Words of length L, they're 2 to the L of them. So the literal description of the process would have an infinite number of probability amplitudes. That's not helpful. So we're going to try to use the same strategy as before to come up with information measures that give us scalar quantities that capture some interesting properties that have some meaning to us in terms of structure, randomness generation, memory, things like that. So that's kind of the overall. And then Chapter 4 is entropy rates of a stochastic process. We'll cover that today. Chapter 5 was last lecture, just real cursory discussion of codes, decodable codes, the Kraft inequality. I did modify the slides based on Tom pointing out some ambiguity in how the Kraft inequality gets applied to characterize the word lengths of prefix codes. And then Chapter 7, which is the channel capacity idea we covered. So that actually takes us up to about the first 150 pages of Cover and Thomas, which of course, I realize that's a lot of reading. I'm trying to give you sections, suggested sections to dip into. I think a quarter-long course in information theory would probably just cover that stuff, and we're doing it in 2 weeks. So, but not going into as much detail because we have other fish to fry. We have other questions. Like I said, we want to understand how to extend these ideas to complex processes, complex time series. Okay.
Question?
Yeah.
So what was the solution to the Kraft inequality?
Oh, I think the thing I boiled down to that was most confusing and that I changed was that there was a slide that said you have a prefix code if and only if it satisfies the craft inequality. The craft inequality doesn't tell you what the code words are. It's a constraint on the lengths of code words. That's all. No comment. So the way you should think about a prefix code is that example when I showed you a tree, and just by putting the code words on a tree necessarily builds in no shorter word being a prefix of a longer one. So you just do that first. And then it was really a second issue, how that tree structure leads to this craft inequality, which is just this constraint on code words. And then we did the Lagrange multiplier problem to recover the notion, the intuition that we should assign short code words to the most probable messages coming in. And that was the derivation, kind of coming back to what you'd already sort of discussed informally beforehand. So that really should have been the way I presented it. Not this kind of lockstep craft inequality, right? Like Tom said, you could have code book with code 1 and 1, and that would still satisfy the craft inequality, but wouldn't be a prefix code. But there are codes like that. You just have to look ahead a little bit that can have a little bit of ambiguity. So I just picked out the prefix codes, and there's much more discussion of Huffman codes, Shannon-Fano codes, and all that sort of thing. That's really the bread and butter of a lot of the application of information theory in building codes. For compression, we wouldn't have video on the internet if it weren't for information theory and this concept and system is, systematically thinking about what compression is in terms of entropy rates completely drives how people build up these so-called video codecs, coder-decoder systems. We're using it right now, broadcasting to Berkeley. The high definition recording of this is for an hour and a half. It's about 20 gigabytes. I'm not posting that. What I do is I compress it down, and there's this little estimator that actually tracks the entropy rate, and I change the frame rate and make a smaller resolution. So what I put up is not the 1020p 20 gig thing. It's about a gigabyte file. That's called 720p, 720 lines, progressive frame rate. There are just tons of these different video compression schemes, all different strategies, different ways of spend a lot of time up front. So when you're looking at a Netflix video, they spend a lot of time, a lot of crunch time taking those videos, or even if you're like reading it off of a DVD disc for a movie, compressing it so you have good quality. Also, so that the decoding process is very fast. Right? I mean, you wouldn't want to click on your Netflix, Breaking Bad comes down, and then you have to wait for 3 hours for it to decode the data coming in. So those encoder-decoder systems have a number of different practical trade-offs. Fast decoding, high resolution. That typically means there's a front end, a lot of computing you do to find the regularities and squeeze those things out to get down to the real entropy rate. The target would be sort of the entropy rate of your TV show. Okay, so, right. So how are we going to deal with arbitrary, complex stochastic processes, time series, sequences? The main strategy is we're going to use the Shannon entropy. And of course, the way we start off characterizing a process is in terms of the word distribution. So what we're going to do is just simply look at the Shannon entropy information in words of length L. And I'm going to call that function h of L, just to kind of simplify the notation. I can drop the probability distribution. Just think of h of L. But again, if I plug in words of length 3, I get a number back, 5.2 bits. I plug in, actually it should be 2.3 bits. If I, length 5, I'll have, say, 4 bits or something like that. So we're going from all these probability amplitudes down to the scalar, and we're going to study the properties of this Shannon entropy in words of length L as a function of L. And that's going to lead us to define some new quantities. In particular, the most novel things we'll run into next week, which will be ways of just looking at the shape of this function as it grows with longer and longer word length and be able to pull out measures of memory, also measures of how observers synchronize, just from the shape of this now scalar curve as a function of word length. So, okay. But the definition is very straightforward. We just have our Shannon entropy P log P formula, and we have this new distribution. We just plug it in, right? Shannon entropy is a function of a distribution. We plug it in, gives us this real number out. Okay, so a few things you can say about the behavior of this block entropy function. It's monotone increasing. So the entropy of longer words, well, basically doesn't decrease. The way to think about this is if I had some joint entropy, a joint distribution, if I add another random variable, at best it adds no new information. Typically, there'll be some more information there. So you add on more random variables, there's more uncertainty. Okay, so this thing grows monotonically with L. And also there's sort of a boundary condition. If I haven't made any measurements, if I'm not looking at words, then the h of L function is 0 at length 0.
Is that, I don't know, part of me that wonders whether it has to be monotone increasing. If you come up with some process that says, like, you can only have length 10 words with an even number of zeros and ones.
Right.
At that point, when you hit length 10, you have fewer choices than you have.
Right, so keep in mind, right, so what we're looking at here, that would be a non-stationary process. We're looking at stationary processes. So if right, you can't have, how to say this, if I've seen a word this big, I've seen all the smaller subwords in it, right? And that leads to this property of it being monotone increasing.
Okay. Maybe I'll have to go play around with it too.
Yeah, I mean, you can define at least a set of strings where.
I feel like you could constrain your.
Sure, where all words of length 1 up to 10 are in this set, and there are no words of length 11. That's not a process, the way we're defining it. So that's one difference. In fact, that's one difference from how folks in computer science think of formal languages. Right? We're imagining that these processes just go on forever. In formal language theory and automata theory, there are these notions of final states that can preclude, even if you sort of saw a sequence of some length, there can be some new restriction that occurs that makes the whole word invalid. So this is in some sense, yeah, stationary ergodic, there's that word, stochastic processes. This is true. And then the statement here is just, I have a joint distribution, joint entropy, and if I add another random variable, the worst, best, the only, the extreme case would be that it's completely predictable and adds nothing to the uncertainty, but typically, you add another random variable, there's more uncertainty in the entropy. This block entropy would increase. Okay, and there are also crude bounds we can come up with. So one way to think about this would be, if I'm looking at length L words, this joint distribution, I have some alphabet, say it's heads and tails, and they occur with equal probability. So as I add on new symbols, looking at longer and longer words, they're independent and their entropy rate would be maximized at just log of the number of events in the alphabet, number of symbols in the alphabet. So the growth rate of h of L would just be linear in L. So if this was, fair coin, that would be an alphabet of size 2. I'd be adding 1 bit. Every time I add on a new random variable, new fair coin flip, I'm adding on 1 more bit. So h of L is just going to grow linearly with L. Or it could be that you have a bias coin. So that would be an upper bound. If there's actually some bias, heads and tails aren't equally likely, then that's not going to be the entropy of that IID process. You can take into account just the entropy of single symbols, L equal 1. But the net result is it still grows linearly. So that's a bound. And we're basically looking at this joint distribution, which is the random variables for words of length L, and make various assumptions about how this joint distribution factors into a product, or the probability distribution factors into a product of individual symbol distributions, IID, or in the entropy way of looking at it, that this breaks down into a sum of the random variables at each time separately. The marginal distribution over just the symbols of length 1, and so on. Okay. But I really want us to think graphically about this, because it's going to help us. So we'll be looking at these block entropy curves. And again, the exercise here is a function of word length. We want to look at this block entropy and look at its shape. So I've kind of drawn a kind of generic shape here. And what I just argued for these bounds was that we have this one upper bound, so the upper bound, where I assume all the symbols are equally likely, they're maximally random, and then this will just grow with, h of L just grows linearly with L, or we can take into account, be a little bit smarter, we at least estimate the probability of heads and tails. Take that bias into account, and that can lower it from the fair coin case, and that'll just grow with L times the single symbol entropy. And those would be correct for independent identically distributed, but we have this general case here that we don't know. There might be restrictions coming in at length 5 in admissible sequences that actually lower the entropy rate. And the question is, what can we learn from the shape of that curve? So today I'm mostly going to talk about the asymptotic shape, if you will. A couple examples, I basically just mentioned them. So fair coin, we know exactly what the word distribution is. So hopefully at this point, you can now take this distribution in your head, plug it into P log P. Well, basically, one way to think about the fair coin is all the symbols are independent and they're equally likely. So one way I think about this is, oh, if my events, even if they're words of length L, if they occur with equal probability, then that P log P formula reduces to log base 2 of the number of events, or the number of words. Right, that was the upper bound in general for the Shannon entropy of a distribution. It's maximized when the events have equal probability, and then log the number of events. Well, they're 2 to the L words of binary words of length L, log of that is L. Okay, so it just grows linearly. Bias coin is similar, and you can work this out. It's a good little exercise, maybe not quite so obvious how to take, right? We can write down this binomial distribution exactly. So we have the word distribution for bias coin, all the words of length L, where N is the number of heads. Okay, and you plug that in to P log P. So it's a good little exercise to do, and you end up showing yourself that the block entropy curve is linear in L, and then there's this coefficient, which is the bias of each independent coin flip, the entropy of that. In fact, this picture we have, these two pictures, linear growth, this is going to be true for any IID process, right? Why? Because by assumption, we're looking at words of length L, that's this joint distribution over L random variables. On the IID assumption, they're all independent. So we just look at them individually, and they sum up. And they're identical, so they contribute the same uncertainty at each symbol as at the beginning. So again, like I probably said before, a lot of work in statistics assumes IID processes. We're basically just, this is it. This is our, they're not very interesting from this information theory point of view, or they're easy to characterize, I should say. Another case would be it's a period 2 process, and I'm just giving you examples to kind of get some idea of different shapes of the H of L curve. So 0, 1, 0, 1, 0, 1, well, we can, of course, write out what the word probabilities are. So 0 and 1 occur with probability half. And if you don't know anything else, and you look at this period 2 sequence, and you just look at statistics over length 1 words, it looks like a fair coin, right? So 0 and 1. But now, when we go to length 2 words, we know that 0, 0, 1, 1 don't occur. The remaining words, 0, 1, and 1, 0, occur with equal probability. We go to length 3, well, basically, there are 8 binary words that could occur, 6 of them don't, and only these 2 occur, and then with equal probability, and so on. So for a periodic process, you look for sufficiently long words, the number of words that are generated are given by the period of the process. And that also means that what happens is when we look at the block entropy curve, it initially grows, and then at some point it flattens out as soon as the distribution becomes constant. And in fact, it levels out right at log of P. Again, why? Well, if I'm looking at sufficiently long words, longer than the period, I just argued that period P process only has P distinct words that occur. They all occur with equal probability. They're all shifts of each other. They all occur with equal probability. So now I have P events, equal probability, plug that distribution into P log P, and it's log of P. Okay, so Maybe it's a period 16 process. I'm looking at words of length 1, length 2. It's kind of growing. I'm still seeing some uncertainty, more and more entropy and uncertainty as I look at longer words until I finally get to the period, and then it just levels off. It's constant from that point forward because I have p events equal probability, and then the value is going to be log of p. So we was kind of done all the basic cases here: periodic processes, bias coin, IID processes, and this is what we can learn from them.
Hey Jim, can I ask you a question?
Absolutely.
So maybe a naive one, but if you're sitting on a sequence of words or a sequence of characters and you get to the period, the next symbol, it seems like you're still going to have some bit of entropy in there, right? Until you realize that you are starting to repeat. So
Yes. Yes.
So it seems like this doesn't. It seems like you're looking back. You've got some information about sequences beyond the current time.
Well, right. Or another way to think about that question is if it's periodic and my window that I'm looking at is long enough, suddenly it's completely predictable. There is no uncertainty given that I've seen some part of the word. If I have enough of the history I'm looking at, the next symbol is going to be predictable. So there's no new information gained in a kind of relative sense. Now, I have to say, and this is a little bit what your question is, Chris, that this is just a kind of a cartoon picture here. It's certainly true what I was saying in terms of this leveling off. So the block entropy will be log p out here. But how you get here actually is quite subtle and interesting. So we'll talk about that a bit later when we talk about synchronization. In fact, I probably should put kind of a squiggly curve in here just to kind of indicate there are different ways that you can get to this flat asymptote. But the basic idea is simple, right? At least for sufficiently long words, in particular L larger than P, you just have P words. They have all the probability, and they each occur with equal probability because they're all permutations of each other because it's periodic. Therefore, the block entropy is log P. Okay, so that's just to, I guess, give us some boundary cases to think about how the shape of H of L could indicate some things. If I just gave you an H of L, well, then, and you saw this behavior, then you'd look out here and say, oh, the period is P. You could look at the shape of that curve and infer what the period was. But of course, we're interested in kind of the general case, and their general case much more interesting. So the first thing that we'll look at is the large L limit of the block entropy. Essentially, the growth rate of that. So we've already talked about, when we first introduced Shannon entropy, we talked about having a random variable, say x, and what its entropy weight was. But that, in a sense, assumed that we were sampling from this random variable in an IID way. And here we have words where correlations and randomness sort of come in different ways as we get longer and longer words. It's not IID. So we actually have to extend Shannon's notion of the entropy rate beyond the IID case that it was introduced in Cover and Thomas. So what we're going to do here is look at the different ways to think about this, the ratio of the block entropy to the length. You could think this is like the average. The number of bits in words of length L divided by L, that'd be like a density or a rate. The other way to think about this graphically is this sort of generalized monotone increasing H of L function comes out here, but at least at some point, the slope becomes constant. And that's called the source entropy rate, H mu. So again, the difference here is that the way the idea was introduced, it was really assuming IID sampling, IID process. Here we can't do that. We have to look at longer and longer words. And then we characterize how random the source is by this entropy rate, and it has units of bits per symbol. Right? Bits per symbol. So it's the asymptotic growth rate of the entropy. It's basically the slope of this curve for sufficiently large L. Notice the way I've drawn this curve, the slope, the local slope is changing. So there'll be some class of processes, most of the ones we'll study, where this slope eventually becomes a constant. And we'll talk about how we get there. You can also argue that this is, once you sort of look at sufficiently long words, you've taken all the correlations into account, this is the sort of irreducible randomness in a process for general process. Sometimes you'll hear people talk about this. It's the description length per symbol of a process. That chapter 3 in covariant Thomas, the asymptotic equipartition property, gives an interesting interpretation of this entropy rate. In particular, there's this notion of typical sequences. So this is sort of a use of this. Once we have this number, h mu, kind of the typical sequences that you see, their probability decreases exponentially with length with this coefficient of h mu. Right? Again, think of the base cases. If I had a fair coin, equally likely, h mu is going to be 1, right? Because we just argued h of L grows linearly with L, so that just gives me 1 out here. So that means that for the fair coin, the sequences that we see, pick any one, doesn't matter, the probability of seeing a given sequence decays exponentially fast with the length. Right? What's the probability of seeing 10 heads in a row? 2 to the minus 10. Like any particular sequence has that scaling with L. More interesting is the case of the bias coin. Right? Remember with the bias coin, 60% heads, 40% tails, there was that little puzzle when we first talked about the word distribution where the most probable sequence is all heads. Right? But it's very rare that you see 10 heads in a row. Right? So what you can do here to kind of characterize, say, well, what set of sequences am I seeing? Well, I'm seeing the set of length 10 sequences that have 60% heads. That's a class of sequences. And every sequence in this so-called typical set, the sequences of length 10 that have 60% heads, their probability goes as 2 to the minus L times the binary entropy function, h of 6040. So this is kind of like, it's like a, we're looking at sets. As L gets large, there are infinite number of things, so we can think about this question, what size is this set? So h mu kind of gives us a measure of the size of the set, where it's really kind of the growth rate of the number of sequences. Or in this interpretation, the decay of their probability of this quote typical set, of the sequences from a source that are typically produced. It's the largest set that captures most of the probability. So that's why reading chapter 3 is interesting and important. It's probably the deepest idea in information theory. Okay. So much for the sidebar. Well, if we're thinking about this entropy growth curve just in terms of the large L slope, well, why not just calculate a slope? And there's a way to do that with entropy quantities. So I could just go up here and look at words of length L and L minus 1 and look at the difference. And that would be like a 2-point approximation of the slope. And we can write that down by just looking at the difference of the block entropes. Simple enough. Well, these are block entropes. And we can use our information identities to rewrite the difference as a conditional distribution, a conditional entropy. And this gives us a kind of a different interpretation closer to how we think in terms of predicting the next symbol. So this is just a simple information sort of joint probability factoring exercise to go from the difference of the 2 block entropies at different lengths to this form. But what this is saying is that we have now this other estimate at a finite L of this entropy rate slope. So it's a 2-point estimate. And it's the uncertainty in the next symbol having seen the L minus 1 symbols. It's the uncertainty after I've conditioned on having seen a past, what's my uncertainty of just the next symbol. So this gives us this kind of a measure of the predictability of a process. Sort of boundary conditions here. If you haven't looked at anything yet, then sort of anything could occur. So we put this h mu of L up at log of the alphabet size. Pretty easy to see that h hat of L equal 1 words, well, that's just h of 1 minus h of 0. We agreed that big H of 0 is 0. So the first value of this is just the single symbol block entropy. Now this is monotone decreasing. So, right, remember h mu is the infinite limit, and because it's monotone decreasing, this as a two-slope approximator converges from above to the true entropy rate. And the way to think about this is, remember, in terms of this conditional entropy expression, as you condition on more and more things, you have more knowledge that can't make something look more unpredictable, right? So it may not help if you condition on a longer history, but it can't suddenly confuse you. So this decreases as I condition on longer and longer histories. This is just kind of re-expressing things. So now I have, at least initially, this other definition of this two-point slope entropy rate hat. That's just a limit of long L's of these approximation, two-point slope approximations. Well, the way I was thinking about this is in the conditional entropy form, right? The uncertainty, given that you've seen L symbols in the past, what's my uncertainty in the next symbol? Or I can just kind of rewrite that if I imagine I have these semi-infinite pasts. And this kind of condenses down this notion of whatever I've seen in the past, the asymptotic condition on the infinite past, what's the sort of irreducible uncertainty in the next symbol. So uncertainty in the next measurement given the past. The geometric picture is it's just the asymptotic slope of the block entropy. And you can show that the original block entropy over L definition and this conditional entropy definition agree at infinite L. Right, so I have two, if you'd like, estimators. I could just take the block entropy at length L over L, or I can calculate this conditional entropy given L minus 1 symbols in the past, try to predict the next symbol. Asymptotically, those will agree, but they can sort of get to the asymptotic true value in different ways. In fact, this approximator, it converges much more quickly, and we'll explain why in a bit. Okay, okay, so that's kind of general process talk, right, without saying too much, and it's sort of more concrete if we have some models. So it turns out there are closed form expressions for a number of the process classes that we've already talked about. If I have the model, do some calculations, I can calculate the entropy rate. So how are we going to do this? So let's first look at the kind of simple case. So we have a Markov chain over states V, transition matrices, state-to-state transition matrices. Well, we're looking at this length L approximator of the entropy rate. Well, that's this conditional distribution, right? What's my uncertainty in the next state, given I've seen some history of states? Well, it's a Markov chain. It's order 1. Therefore, the next state only depends on the immediate preceding one. Chop that off. Well, what's this? Well, down inside, this conditional distribution of next state given the previous one, that's what the transition matrix gives us. So we can calculate h mu directly from that. What we have to do is we calculate the asymptotic state probabilities over this. Using the transition matrix, we look at the left eigenvector, normalize that in probability. And then, so the closed form expression for the entropy rate for a Markov chain is just, think of it as the state averaged transition uncertainty. I go to each state, state B, and I look at the transition structure. How many states can I go to? C, D, and F with equal likelihood. Then there's a transition uncertainty, and then I just weight that with the state probability. So again, this is calculated directly from the transition matrix, left eigenvector normalized in probability. So that tells us how probable the states are in the Markov chain. And then we just look at each state, and if I had 2 outgoing transitions with equal probability, well, that would be 2 events, equal probability. That would just be log base 2 of 2 would be 1 bit. So every time there's equal branching, I get a contribution of 1 bit. If the next state is completely determined, D always goes to F. There's no uncertainty, and contribute no information from that state, and then we just average that. So it's the state average transition uncertainty. So not too hard. Maybe there's a little linear algebra to do here. Calculate the eigensystem for the transition matrices. And the base cases here are easy just to read off. So let's just talk through these again. So the fair coin, right? We already sort of worked through that the heads and tails are equally likely. Well, by definition, we have the transition matrix here. So we know each state, heads or tails, is fair probability. So I go here, I'll be in state H with probably half. I'm looking to the future, I'm either going to come back to H with probability half or go to T with probability half. So my uncertainty is exactly 1 bit because there are 2 events in the future, heads or tails, and they're equally likely. Same thing here. So I have 1 bit contribution here, but I only hear half the time. 1 bit contribution of transition uncertainty here half the time, but that adds up to 1 bit per symbol. Bias coin, same thing. If you remember, when we calculate the asymptotic state distribution for this, the heads, asymptotic state probability is P, tails is 1 minus P, so that we have that. And then our uncertainty in each state is just the binary entropy function, H of P. H of P here, where I'm going. So we have 2 contributions of that, but with probability half, so we end up with the bias coin entropy rate being H of P. We already kind of knew this because these are the IID processes that we first introduced, okay? Period 2 process, well, okay, so I'm in states A or B with equal probability, but the transition uncertainty is 0 in each state. I know exactly where I'm going if I'm in state A and where I'm going if I'm in state B. There's no uncertainty, therefore it's 0 entropy rate. More complicated machines, which we're going to deal with, more complicated models like this, are just combinations of sort of local branching uncertainty and some determinism. So mixtures of these cases. So more interesting for us would be to think about hidden processes, so hidden Markov chains. In particular, and this is now going to maybe help clarify why we focused on the unifilar hidden Markov chains. So remember, unifilar means that in each state, the symbol determines what the next state is. And the benefit of that was I have my process that has been generated, and I'm asking a question about the information in the process, say the 0s and 1s coming out. But because of the unifilarity, there's a mapping between observed sequences and internal state paths, which means I can use the internal Markov chain transition matrix to calculate an entropy rate that's certainly true for the state sequence, the hidden state sequences, but it's also true through unifilarity of the observed sequences. So we end up with a very similar formula to the one I just showed you. Except now, of course, again, we're asking if I'm thinking about, right, I have some internal Markov chain transition matrix, and then I have a different observed alphabet, 7 internal states and a binary output alphabet. And that's what I'm interested in. I have this binary process. I want to know what that is, but I can use essentially the entropy rate of the internal state Markov chain, suitably modified, but the same idea. I calculate the internal state asymptotic probability, so I have a state average quantity, and then I just look at the branching uncertainty in terms of the symbols that label the edges. But it's very similar to the previous formula. And this formula only works because of unifilarity, because we have this tight mapping between observed sequences and the internal state sequences. How about getting back to our prefix code example? Use this notion of entropy rate for something that's a little bit non-trivial. So this example every year makes me see more and more data. There was a time when one had to call up over a telephone to get to the campus computing center, right? Good. Some of you are smiling. You've heard about this. You'd have no direct experience of this. And of course, if you were at home, in your communal household and you're typing away on your dissertation, and then someone else picks up the phone, your housemate picks up the phone, they screw up your entire communication. This is bad, right? But one of the things you would have noticed is that when your housemate picked up the phone while you were online, as you were typing, these great words of prose for your dissertation, it sounded noisy. It's like, what do you mean? Why should it sound like noise? So here's the reason why. And this is generally true about pretty much all communication systems. Okay, so we have, my dissertation, I'm writing it in the 4-letter alphabet A, B, C, D, and we had, our not a very sophisticated dissertation here. A occurs at probability half, and so on. The entropy rate was 1 3/4 bits. We chose this code book. We sort of talked about how it was optimal. But now I have this question, right? There's this box, and I'm busy typing away. It's encoding my ABCD text into a binary string. So that's a process. It's a binary process. And I want to know what the entropy rate of that binary process is. I know what the entropy rate of the input is, of the messages. We just calculated that. It's an IID process. We're sampling from X IID, so we know exactly. But now I've changed to a 2-letter alphabet. What's the entropy rate of that? Okay. So remember our prefix code book. I'm going to turn this into a little machine that gives us a kind of a hardware implementation of the encoder. So the way we're going to think about this, right, the encoder is going from ABCD to binary code words. So how does it work? So what we're going to do here is imagine that we start up at the top of the tree, and depending upon whether I see A, B, C, or D, I follow one of 4 paths. A, I go down this path and emit a 0. That's the encoding of A. And that's going to happen half the time, given I see A half the time. If I see a B, we go down the tree along this path, emitting a 1 and a 0. If it was a C, it was 1, 1, 0, and if it was a D, it was 1, 1, 1. Right? So the symbols along the tree links here are what gets emitted. And then, of course, once the machine, the encoder, is done, think of it as like falling off each leaf, it resets and waits for another A, B, C, or D to come in and does the whole thing again. Okay, so now we're getting close to a state-based model, right? I'm kind of describing a mechanism that's visiting states repeatedly. So here's how we can think about that. There are these internal states of this mechanism, this box I'm just designing, call these big A, B, C. And then here's a exactly same equivalent, I should say, just hidden Markov model for this encoder. So, and I'm denoting starting at the top tree node just here with this little double circle, okay? So if a little a comes in, I do this. If a b came in, I do this. 1, 0 is what I output. Little c would be 1, 1, 0, and d 1, 1, 1. And then comes back here and it's ready to go again. So the machine resets back to this start state. So we know how to analyze this. Well, we have one little property check. Is this a unifilar model? Right, you just have to go here. So if I'm in A, 0 takes me here, 1 takes me there, so that's fine. B, 0 goes here, 1 goes here, so the next state is uniquely determined by the symbol on the output edge. And then here, well, either 0 or 1 take me to A. So the next state's uniquely determined. So it is unifilar. Therefore, we can calculate now, using the formula I just gave, the entropy rate of the output binary process from this encoder. Well, okay, so they can work through, in a different form, that graphical label-directed graph. This is the transition matrix of the internal states. Then you have to go calculate the left eigenvector. That's 4 sevenths, 2 sevenths, and 1 seventh over the internal states ABC. You can also split this out for the edges in the state transition to labeled 0 or labeled 1. The test for unifilarity here is really simple. You have at most 1 non-zero component in each row. If there were 2 positive components, that would mean on the same symbol, you're going to 2 different states, so that's not allowed. So that's easy to check here. But now we can just plug this in to our formula, right? So it's a state-averaged branching uncertainty. We calculated our asymptotic state probability, 4 sevenths, 2 sevenths, 1 seventh. You can just plug that in. Well, notice that the way the tree got built, that in every state the branching is equally likely. Branching's equally likely. So that's easy. In every state, my uncertainty about the next state is a fair coin. So 1-bit contribution. So it's really just I have a 1-bit contribution from each state, and then I'm just weighting that by the state probabilities, and that's 1 bit. Okay, so I started with this 4-symbol kind of biased alphabet. I chose these optimal code words. It's this prefix code. Built this encoder, and it has turned that 4-letter source into a fair coin. So you might say, well, wait, they just wrecked my dissertation. There's nothing left. But it's decodable. So I can unpack it and get back to ABCD. So actually no information was left. The benefit is that if I had now some communication system that only took a binary alphabet, I could plug this in and use it to transmit that and then decode at the end. And I've compressed it because the original 4-letter alphabet source was biased. A was very probable. So I've gone from this distribution of very biased down to something that's completely uniform. And we just showed that is essentially a fair coin. It's 1 bit per symbol, uncertain. So the other way to say this is that if I have a binary channel, this encoder will use it to full capacity. Right, we had this notion of redundancy. Right? It was a difference between using the original 4-letter alphabet just on its own. So we had 4 events. So log of that would have been 2 bits if I was using ABCD. But now, actually, we just showed that the actual message entropy was 1 3/4 bits. So the encoder has, in a sense, extracted a 1/4 bit of redundancy from the original 4-letter source. And in doing so, it produces this fair coin output. So that's why the modem sounded noisy. That's why if you were to interrupt any transmission system, if it's a good one, optimal in a sense, it's going to be using all of the communication channels bandwidth or using it fully by being as random as possible. Right? So when I compress an information source down, if I do that optimally, and we know what the goal is, right? That's the entropy rate of the message source. It will look like a fair coin or a fully random process. That's the measure of optimality in encoding. So, yeah, so that's sort of goal. You want, when you compress, you want the result to be just the really informative bits, not the predictable things, right? U follows Q, that's predictable, more or less. So you can factor that. That's a rule that both the sender and receiver can use to factor it out. Okay, so now what's the sort of flip side of all that? What's the entropy rate for a non-unifilar hidden Markov model? Well, it's simple message. There's no closed form. This is a hard problem. This problem was, Shannon's first work was published in 1948. It wasn't until about 10 years later people realized that there are a whole class of even finite memory, finite state sources that are non-unifilar that you can't write down closed form expression for the entropy rate. Kind of odd or unfortunate. In particular, the formula before just doesn't work. You can't, the entropy rate of non-unifilar source just is not given by that expression. You can do this, right? I have states. I can calculate their asymptotic state probability. I have the transition matrices, but you apply this formula to what you're given, but in a non-unifilar case, it doesn't give you the correct entropy rate. Again, why? Because there's this huge mismatch in the non-unifilar case between state sequences, the entropy of which is really controlled by the transition matrices, between that and what you're observing. So typically, this will be an overestimate of the actual generated process's entropy rate. So Cover and Thomas do mention, kind of on a side, the end of one of the chapters, it's chapter 4, that you can provide upper and lower bounds on the entropy rate estimate for length L words, but you have to know the internal states, which is kind of unrealistic. I mean, if you've designed the apparatus, then okay, maybe you have access and stick your head in the box. But if I just gave you a process in terms of word distributions, what's an internal state? How can so I couldn't even use this part of the bound because I don't know what the states are. Binary alphabet, maybe the thing has 100 internal states. I don't know. It's non-unifilar, you're stuck. So, but it turns out that there's a way, A, to figure out what the states are, the effective states are, in such a way that we can actually use this formula. But we have to, this is spring quarter, we're going to come back, figure out how to go from a given process to reconstruct the sort of effective hidden states. And then once we have these hidden states, it turns out the model we get in this is going to be unifilar. Might be infinite number of states, but it turns out that's okay. And we can basically apply this notion of state averaged uncertainty, transition uncertainty, and therefore estimate the entropy rate even of non-unifilar hidden Markov models or processes produced by them. So that's a little sort of looking forward, but we need some more, more technology to get there. So there is a, at least at where Cover and Thomas leave it, it's an open question, unsolved. There's a solution. But we have to kind of open up a little bit and talk about modeling and what do we even mean by states before we can come back and do this. But anyway, now, I mean, so we at least, sort of at this point, what we've done is talk about these entropy growth curves, and we're just looking at the asymptotic growth rate, which we interpreted as, assuming we can get it somehow, it's the irreducible randomness in a process. Even if we had infinite histories, stochastic process will have some residual uncertainty in the next symbol. So, very important property. In fact, it was Shannon's notion of the entropy rate was brought into dynamical systems in the late 50s to use it as basically the first measure of how chaotic systems were. So there's this sort of long history and actually now fairly deep connection between this view of information and processes and how chaotic dynamical systems are, right? So there's kind of this tension between, I mean, the last week or two we've been talking about stochastic processes here over discrete alphabet. Well, okay, if we designed our instrument right with a generating partition or Markov partition, then it's going to tell us something interesting here. But we did have this other notion here of why chaotic systems are complicated, right? It was this stretching and folding, the complicated orbit sets. So, right, we have this sort of geometric notion of degree of instability captured by the Lyapunov exponents, right? The kind of averaged over the invariant set, stretching and contraction. And now we've got this other sort of notion over here of entropic uncertainty. How are these things related? Kind of a notion of predictability there. So what's the connection? So that's what I want to talk about now. Sort of the rest of the lectures to try to tie the information theory back to the original dynamical systems. So again, just a quick refresher. Remember what we were doing anytime we have a discrete resolution or precision instrument, we're coarse graining the state space somehow. If it's a good instrument, then we end up with going from the dynamical system itself, state space mapped to itself under discrete time map or flow in a differential equation. Then we go through the measuring instrument down to the space of symbol sequences, just trivially shift in time and then map that back. So the idea is that good measuring instruments allow us to either look at the dynamical system directly or go through the symbolic representation, and either way is a faithful representation of the behavior. Right? The other way that said that the diagram commutes. So assuming we have good instruments here. So now the connection between the sort of symbolic dynamics and the information theory is we can talk about, if we have some dynamical system, think Rissler-Lorenz or the logistic map or tent map, we have some invariant measure, some invariant set and distribution over that. We can just sort of choose, we sort of think of our measuring instrument as partitioning up the space into discrete cells, and we can look at the probability in each one of those cells. Each cell contains some part of the invariant distribution, and then we can calculate the uncertainty in that. How uncertain as to what partition element we're in. That's the Shannon entropy of a partition. So that's kind of notation here. Script P is some partition. And then there is this quantity. I'll denote it H mu for reasons that'll become clear at some point shortly. This notion of the metric entropy, it looks at, remember how we could refine those partitions? If you look at longer sequences, the partitions got refined. So now you have to imagine finer and finer partitions as we look at longer and longer words here. And then we can look at the entropy, applying this, that's in this partition, refined partition. And then we look at its growth rate. So that's called the metric entropy of the dynamical system F here under this partition. So they're good partitions, they're bad partitions, generating Markov, whatever. So what Kolmogorov showed is that if you look at the largest metric entropy given a partition over the whole space of partitions, so this is a bit non-constructive, right? You're taking the largest value over this big space of all the different ways of coarse graining your system. That is the entropy rate of the original dynamical system. Right. We talked about two particular kinds of partition that we knew immediately were good Markov for generating. And here he's just talking about general dynamical systems. So, and what this development tells us is that this entropy rate here, this metric entropy, is really how the dynamical system is taking parts of the state space and mixing them together, stretching and folding and putting them back to again. Kind of on a macro scale. I coarse grain the system, kind of, then the dynamic sort of induces the transition and stretching of this coarse grained probability distribution, just like when we talked through with the, say, the Markov partition. So now, in the happy case, so this supremum maximum is reached when we have, if we're lucky enough, to find a Markov partition or a generating partition. But the theorem holds in general. Sometimes you have to have, very, very refined partition and so on. But this is a way of measuring the sort of, now, this sort of prediction uncertainty in an information theory way. And then Kolmogorov wanted to show that that was a good way of distinguishing the degree of chaos of different dynamical systems. Again, so then the flip side was this very, head inside the box, this notion of the spectrum of Lyapunov exponents, right? So it's been a while. So the picture here was we have some reference trajectory, and we can imagine we have this little basis set, and then we look at, so this little basis set or frame is carried along the reference trajectory, and then we look at how the basis vectors rotate and shrink and stretch. And that was the sort of time average shrinking and stretching captured by the Jacobian, the local linearization, that gave us the spectrum of Lyapunov exponents, right? So we had an n-dimensional dynamical system. We have n exponents. Typically, we order these from largest to smallest. And then that will give us that classification scheme you worked out in the midterm. But this is very geometric, right? The idea there was the picture is, as in one of these chaotic systems, there are directions of contraction. Your neighbors are coming towards you in some subspaces, and other directions where your neighbors are moving away from you. And there's this one-to-one correspondence between these submanifolds of instability. They're associated uniquely with positive exponents, and the contraction directions are associated with negative exponents. But that's a very geometric picture of what's going on. And it's closer to our notion of, chaotic systems produce complicated sets of orbits. So the connection, and it probably would take like half a quarter to prove this, is that this metric entropy, or I'll just say entropy rate from now on, is equal to the sum of the positive Lyapunov exponents. There can be lots of negative ones, lots of stabilizing directions, but the positive ones are related to this. So this is an interesting connection between what was essentially a kind of a global view of how the dynamic operates on coarse-grained sets and maps them into each other. And that's sort of exactly the same, or dual to how sort of locally the system is stretching and shrinking. Or in fact, what's just related to the stretching directions.
Hey, Tim?
Yeah.
Can I ask a question?
Yes, please.
Okay, so I guess that between different
You're dropping out.
bits of information or something like that,
Try again.
No.
The sound.
Yeah, the sound was dropping out, so I would get the first word or two, and then it just.
Sorry. Yeah, we had some feedback here, so I turned it to
Oh, I see. Okay. Yeah, we should work on that. More tech.
Never mind.
No, that's really good.
No, you must ask the question. Now you've got us interested.
Okay, so, so, it seems,
Hold on. Jim, can you just mute your mic during this? Because that's what's causing.
Oh, I might be able to do that.
Sorry. Yeah, we just did.
What? Interesting. Why are you? Okay. Okay, now am I back?
Yeah. Please.
Okay, so good question. Right. So what? Okay, so this discussion is just focused on one kind of question, which is we're assuming we're on this invariant set, on the attractor, as it were, and just looking at the information production properties and how that relates to the Lyapunov exponent stretching, and then this sort of coarser picture of how the partition elements are being refined and mapped into each other. Now, the negative exponents, in some sense, all that happened before. So you can imagine, here's my attractor, but I started way outside of it, right? It's a attractor, so I'm going to come back down. It's the negative exponents that are bringing you to the attractor that determine its stability. So again, what I'm talking about here is I'm assuming we're already there, already on the invariant set. But the negative exponents describe if I were to, even if you were on the set, I come and I kick you off, they would give you the rate of coming back to the attractor. So they don't factor into this because we're just talking about what's going on within the attractor. But the negative exponents tell you how you get to the attractor initially, starting from different initial conditions.
okay, so there's sort of like a transient.
I wonder why it's dropping out again, dropping out again. Go ahead. Go ahead.
So,
Am I back? Okay, so right, I see where you're going with that. Right, so the direct answer is when I'm talking about H of L curves, the block entropy curves, it's all assuming we're on the attractor. Now, you can ask questions about how much information is created or lost when I start off the attractor. And you might have a corresponding, you can actually have a corresponding Shannon entropy of that initial distribution. So let's see, I don't know if you saw the dot spreading lecture, but there I was starting a small set of initial states close to each other, then they spread out. But I could have started that initial ensemble, 1,000 initial conditions off the attractor, and then you could track its Shannon entropy. That's a distribution or some approximation of a distribution. And then you can, in that case, have things spread out, entropy would increase, or come back together and decrease. So right now, I'm kind of dealing with a simpler setting, but it's a perfectly valid question. Can I use this information measures over different starting initial distributions? Good project. I mean, you can try this. There's one of the labs that lets you evolve distributions for one-dimensional maps. You can stick in different initial distributions at different places, and you'll see sometimes the distribution will broaden and sometimes it'll shrink. And that would correspond to entropy increasing, entropy of the distribution increasing or decreasing, right? So like for the logistic map, you start the distribution way over near 0 and 1, the slope actually, it's well above 1. R is equal to 4, the slope is 4. But right near the smooth maximum, there's a lot of contraction. And so starting initial distribution there, it gets focused. So the distributional entropy would decrease there. Yeah, so again, this is just, soon as we get the basic information theory tools around, we can apply them in different settings. Essentially, you're asking a different kind of question, but the tools apply equally well. Okay, good. Right, so there's just, it's been quite a long period of time, although if one was reading, for example, the Strogatz book, you probably would never get the connection between chaotic dynamical systems and information theory. It's almost like they're different schools of thought, when in fact, the connection goes back half a century. And it's really important. Like I said, Kolmogorov, lock, stock, and barrel borrowed Shannon's information theory, brought it into dynamical systems, has these more general, theorems about taking the supremum over all partitions, and you get this quantity out that gives the sort of kind of how the partition elements are mixed into each other on average. And it was a bit later that then people related these Lyapunov exponents, the sum of them, to the entropy rate, which is this interesting, on the one hand, very geometric picture of what's going on, local geometric, and this kind of large scale mixing partition elements together. Okay, so actually the last thing I wanted to talk about was this paper I mentioned at the beginning with Leibowitz and Penrose, that review in Physics Today. Partly, I have this interest in classification schemes. This whole field is kind of interested in different kinds of classification schemes. So it turns out there, over the years, have this refined classification of processes has been developed. So this one is called the ergodic hierarchy. Right? We had another classification scheme, like the 5-dimensional dynamical system Lyapunov exponent signatures you put together. That's a classification scheme. Again, all of this is trying to get some handle on how rich natural processes can be. So we try to, now we have information tools and this notion of mixing cells into one another with the entropy rate. There's another classification scheme that came out of this. So sort of at the bottom of the hierarchy is this basic notion of an ergodic system. And what that means is that I can, I'm interested in some property. What's the temperature? Actually, what's the Lyapunov exponent? I can either time average, or if I know what the state probabilities are in the state space, I can do a state space average. So this is this notion of ergodicity. The simplest ergodic system is the harmonic oscillator. Right? If I set the energy in the system, it's going to oscillate at some frequency, and it visits all of those states, and I can either say, oh, along my limit cycle, it's not even stable, on my cycle in the oscillator, all the states are equally likely, so I can either calculate whatever property, average frequency, average state, whatever, either by following one solution or just looking at the probability of being in those states and doing an integral over the distribution in the state space. In the thermodynamic setting, that means, for those who have studied statistical physics, that means you can use a microcanonical ensemble. All of the accessible states at a given energy are equally weighted, which makes calculations easy if it's actually the case. So ergodicity can be helpful that way. Now we have, so the next step up are called mixing systems. And these are more like this and maybe the case of mixing, more like what we were seeing with the one-dimensional maps and the chaotic differential equations, where I might start with a very skewed initial distribution, or some knowledge of where the system state is, but the system eventually goes down to some attractor. Or in the thermodynamic language, you'd say the system approaches equilibrium. So all mixing systems are ergodic, but they're ergodic systems like the simple harmonic oscillator that are not mixing. Right? If I have a simple harmonic oscillator and I start with a bunch, I pick just a few of the states and some distribution, that bunch always stays together. It never spreads out over the whole set. The mixing property allows that and requires this, the metric entropy to be positive so that cells are actually stretched out, fold over, map back onto each other. K system, that's for Kolmogorov. This is a slightly different property. It means the system state forgets its past, forgets its initial condition. So here you could kind of imagine if I had the Rössler or Lorentz attractor, I could start in any number of distant initial conditions. But once I get down onto the attractor, I've forgotten where I started from. So it's slightly different property, it's a little stronger, forgetting the initial condition. That's kind of typical. Chaotic systems are this way. The system that's been analyzed in a lot of detail is the hard sphere gas, simple model of a box of gas molecules where the molecules are just spheres bouncing around. Actually showing that it's a chaotic system, or one of these more technical case system, took one of Kolmogorov students 80 pages to write out the published paper. Actually, it didn't get published for many years. It's just very complicated. But nonetheless, it's an intuitive property for getting your initial condition. And then at the sort of the top of this hierarchy, so this is really kind of becoming more and more apparently random. Then we have like the Baker's map, what's called the Bernoulli system. It really does look like the fair coin, kind of ideal random, fully developed chaos, if you will. So those are the most random. So today, what I've been talking about is really just how to measure degrees of randomness. Right? The entropy rate was this sort of proxy for how, given even an infinite history, what my sort of irreducible uncertainty was in the next symbol, some measure of randomness. Then the ergodic hierarchy is sort of trying to classify different properties, going from sort of predictable up to most unpredictable. What we're going to start doing next week, though, is going back to the block entropy curve and using its shape to tell us how much history is remembered by processes. All right, I kind of hinted at that. So today, I was looking at this growth rate at large L. There's this question of how does the system get there as I look at longer and longer words. And that H of L curve can have different shapes. It can quickly get to its asymptote or slowly, and that's going to indicate little or lots of memory. So we're going to turn this around and start talking about properties that are not so much degrees of randomness and unpredictability, but how structured things are. Oh, and then, right, take a look at this article in the Reader. So this is regularities unseen, randomness observed. So the lectures next week will mostly be out of that article. It's a review article, hopefully readable. Okay, so any questions?